So these are under data, NGS. Here's the hammer data, and then here's some other NGS data, GILAD. Same format. I have the count table, I have the pheno data, and I also included a Word document that was included with the publication that gives some more background on the samples and how they were created. Let me get the script. Here's the script. And let's change the working directory to be looking in the right place. Okay, so here's another example. These are RNA-seq data. It's human liver tissue. So liver tissue data. And we have my condition differences being gender. I have 3 females and 3 males that we're going to compare. There's the abstract length. It's the same format that you're going to use in your homework. So you go get that count table.txt and the phenodata.txt and read them in using something like read.table. Here's what you get in this example. I have about 53,000 genes, 6 columns. There's my read counts. So I have 1 row per ensemble gene. Like we've seen in other data sets, there's going to be a bunch of these genes that have 0 counts. Not every ensemble gene was represented in the data. So the first 3 columns are the females, female 1, 2, 3, and then male 1, 2, 3. Here's the group data. So this came straight out of that phenodata text file, and this was just what was available to us in that phenodata text file. Here are the column names of the read counts as they came in from the raw file. I replaced the column names with something more readable instead of SRX 014818 and so on. Now we have F1, F2, and so on. Here were the original column names. There was a column for number of technical replicates. So mentioned before that a technical replicate is just, in this example, you have a human being, a female, and you have liver tissue from that female. You mash it up into RNA, and you split it into 2 subsamples. I run this sample, I run the other sample, I ran that female twice. And what we have are the pooled counts for that individual. Pooled somehow. I don't know if they averaged them or added them together. I'm not sure what they did. But we don't have the technical replicate information. And then, of course, gender in the last column. Let's get rid of the genes that have 0 counts. There were a lot of them, 10.5 thousand that we filtered out. So now we have 42,000 genes. And I'm going to compare those 3 methods that we played with. So EdgeR, DESeq2, and Lemma. And there are some interesting differences between them. So first off is EdgeR. Let's library that in. Remember that EdgeR and DESeq2 have their own construction objects that they want you to use to wrap together the read counts and the group-specific information. So for EdgeR, the object constructor function is called DGE list. So I'm going to create a DGE object. I had to specify the library size. All that means is the column size for each of my samples, the total number of reads for each of the samples, which can be very different when you're doing NGS data. So it's an important factor to account for. And my comparison group, in this case, I just have one or two classes, one factor, one binary factor. I pass in as group that one factor. With edgeR, remember that that method does moderation of the test statistics by, instead of having gene-specific standard deviations, it computes gene-specific standard deviations, but then it shrinks them toward one common number. So the standard deviations are shrunken to make them more stable. That's what's happening here. And then we can do the actual test. Because I have just two comparison groups, I can use edgeR's exact test function. There's multiple ways to do testing with edgeR. You can do this as an exact test, which is like a Fisher's exact test. You do a negative binomial calculation. The probability of getting a count difference of this or bigger equals such and such. I compute that probability. I compute the p-value. There's also GLM-based functionality if I had more than two comparison groups or if I had multiple covariates that I wanted to adjust for. In our example, I can just use the exact test function. Top tags will order the results in terms of one of the summary values. In this case, we're going to sort by p-value. And then I'm going to filter out that result by false discovery rate. So basically get a p-value for every of my genes, my 45,000 genes, and pull out just those genes that had FDR estimates less than 0.1. Here's what I get. That was my first 6 genes ordered by p-value. edgeR out sig. There were 63 genes that had FDR estimate less than 0.1. And there's the summaries for each of them. So tiny, tiny p-values and tiny, tiny FDRs, all the way down through something that's very close to 0.1. So this would be the 63 genes that I would take back to the biological collaborator and say, look more at these genes. These seem to be relevant for distinguishing male and female in terms of liver tissue. Here are, the next step would be to look a little more closely at those genes. I have p-values basically, but it would make sense to maybe look at some pictures for those genes or some summary statistics. So I did that. Here are the gene names. Names edgeR significant. That's the gene names, the row names that correspond to FDRs less than 0.1. And then I'm going to go look at the raw read counts. So capital Y is the M by N matrix of read counts. Show me the read counts for each of those 63 interesting genes. And they look interesting. So here's these 63 selected genes. And if you look through here, something kind of jumps off the page about these. For example, that's the most statistically significant gene. And you're comparing the first 3 counts to the last 3 counts. And there does, if you were to take the average of those chunks, there would definitely be a difference. The last 3 would have a much bigger average than the first 3. But the reason for that is almost exclusively because there's an enormous count in that first male. 1,500 compared to numbers, well, there's a 400, but most of these are much smaller than 1,500. If I look at the second gene, it's the same thing. The first group is definitely going to have a bigger mean than the second group, but almost exclusively due to the fact that there's an enormous count for the third female. Same thing. Not quite the same, but still a big number in that last column. Definitely that condition. Again, that condition, 747 versus the others, 258 versus the others. And when I looked through, there may be some exceptions, but almost every one of them have that going on, which is a little weird. So if you were the biologist, and you're interested in which genes are different between males and females, arguably you don't really care about these genes. These genes are not all that convincing. Do I really believe that a gene that's barely expressed in males and only moderately expressed in females, at least looking at those counts, is all of a sudden turned way up in one of my samples? Why is that third female so different from the other two females? Why is this first male so different from the other two males? And go all the way through. There's not any one sample that seems to be consistently different from the other samples. So there's not like an outlier sample. There doesn't appear to be one sample that just has a bigger library size consistently. There's just this kind of strange outlying pattern going on. And I bet if you were to present this to the biologists, they would not believe these results. They would say, I don't trust the numbers for those genes. So you might consider, as a methodologist, you might think, how can I avoid this type of behavior? One way to try to filter out genes like this would be to do some kind of outlier filtering. These would be outlying genes probably. Or they at least would have, if you looked at these 6 numbers, you would, according to pretty much any algorithm for calling something an outlier, you would say those 6 numbers have an outlier in them. That 1504 is going to be called an outlier. There's lots of algorithms or rules for saying whether something is an outlier. For example, is a number beyond 1.5 interquartile range of the rest of the data. So if we were to do a box plot, here's the middle 50%. Is that 1504 beyond a certain range with respect to that? It's going to be. Any one of these is probably going to have that flag turn up. So I'm not sure why you don't have that implemented in EdgeR. You do have it implemented in DEC2. I'll show you that in a second. So this is a little bit concerning results, even though it came back as saying there's 63 differentially expressed genes. If you look a little more closely, you may not believe that result. We also learned that it's useful to look at the distribution of p-values. I know what it should look like. If the methodology is doing what I expect it to do, I expect a p-value histogram that looks something like this. So a mixture of differentially expressed genes and non-differentially expressed genes. And patterns that don't look like that are indicative of something not quite right. Maybe there's correlation in the data. Maybe variabilities were not estimated correctly. Maybe there's just technical replication but not biological replication, so I'm not estimating the right variability. Just something's not quite right, and there is the histogram of p-values from EdgeR, and there's an enormous peak over here at 1. There shouldn't be. If you filter out the low count genes, which is one possible explanation, it might just be really low count genes, which I can't estimate a p-value well for, so it gets assigned a p-value of 1. It helps a little bit, but not nearly enough. So that's cause for concern. What else do we have? Here are those features that have p-values equal to 1. There's a bunch of them. Almost 2,000. That's why I have such a peak here. There's nearly 2,000 that have p-values that were called exactly 1. And here are the first 100 of them, the read counts for them. So I don't see a really obvious story for why they have 1s. There are several that have really low read counts, so maybe that's why they have p-values equal to 1. But some of these look fine in terms of read counts. So I'm not sure why they got p-values of 1. Okay, so let's quit there before we go into DESeq2. Short story is that DESeq2 finds just 4 genes as being differentially expressed. Almost all of the genes that EdgeR called differentially expressed were given a false discovery rate estimate of NA. or no, 80, yeah, let's see. Yeah, almost all of the genes that were called statistically significant by edge R were actually given p-values of NA by DEC2. And if you look at the documentation for DEC2, it gives NAs for either really low read counts or genes that are called outliers or that have outliers. So DEC2 seems to be do something a little more sensible in this example at least. It doesn't filter, it doesn't bring to your attention those kind of weird genes that edge R did. All right, so we will look at that next time. And then lemma. And lemma is interesting. It has all of its FDRs bigger than 0.95. So again, some kind of odd behavior. You wouldn't expect that. None of the FDRs are less than 0.95. All right, so we'll pick up there on Wednesday. All right, let's get started. Last time we introduced a new data set, so the Gilead RNA-seq data. These were human liver tissue, and we had 3 females and 3 males. Just like with your homework, there are 2 data files. One is the count table data file, so an M by N matrix of read counts for each of the genes. And then the columns are each of the samples or individuals. And then there's the phenodata file, also a text file, that just tells you for each of the columns any phenotypic data that we have, so like covariate data. In our case, what gender, it might be different experimental conditions, ages, genders, whatever, different covariates. So I've read them back into R, and I've dropped out the rows that correspond to ensemble genes that were not represented at all, so 0 read counts. And then we were going to compare the 3 main differential analysis or differential expression methods that we've seen in bioconductor. So edge R, we looked at that already. And one of the things, remember, that we saw about edge R, let's just remind ourselves here. When we did differential expression analysis with edge R, we looked at the top, there were 63 genes that had false discovery rate less than 10%. So we might call them statistically significant or interesting. Here were the raw read counts for those 63, and we noted kind of an interesting artifact about them. I think every one of them has this issue where one of the samples is an outlying value. So like gene 1, there's at least 1, maybe 2 outliers. Certainly that 1,504 read count is very different from the others. Similarly here, the 714 is very different from everybody else. So we said that in terms of like presenting these results to a biologist, they might not they may not like these results because they may not believe that there would be such a big difference sample to sample, individual to individual. But edge R called these genes statistically significant with an FDR of 0.1. And I think last time we did DEC2 also. That's the method you're using in this week's homework. So DEC2 has this transformation that's handy. It's called R-log. We have count data with NGS data, and count data are not designed, or at least like the exploratory stuff that we've played with, cluster analysis, PCA, SVD, they're not designed for count data. So if we wanted to do exploratory stuff like that, it would be nice to have this transformation of the data. So the R-log transformation, basically a log transformation to turn the counts into more continuous looking data. It does it in a smarter way to try to regulate the variability of the genes to be roughly constant. If you don't have constant variance, which you don't with NGS data, you have larger read counts, longer sequences, having more variability. You have more abundant genes having more variability, so there's a mean variance relationship, which can mess up, like if you were to do PCA, where's the variability, where's the biggest driver of variability? It might just be expression level, overall expression level, or it might just be length of the sequence. And we don't really want to pull that kind of pattern out. After doing the R-log transformation, we can do cluster analysis like this. And it'd be nicer if I had the more descriptive sample names here on the dendrogram. I'm not going to bother to do that, but here we have cluster analysis. Looks like there's maybe 3 clusters, so 1 and 2 and 3, although it's not terribly convincing. Here's, we have PCA, and we also have SVD. Here's what SVD looks like. There's not patterns that are just extremely more informative than the others. The top one explains 36% of the variability, 27%, 16, 11, then it flattens out. So I wouldn't put too much into these patterns. This probably is similar to what we saw in the clustering. The clustering said that one sample clustered by itself and another sample clustered by itself. So I bet that's what those were. In fact, I know that's what that was. This is the third female, this is the first male, and they looked marginally different from the others. It's not extreme. Differential expression analysis is done with the DE-seq function. And when we look at the results, again, thresholding on an FDR of 0.1, go pull out all the genes that have an estimated false discovery rate less than 0.1 and call those statistically significant. There's only 4 of them. So it was those 4 genes. Here are the read counts for those 4 genes, and they look much more believable than the ones that we had for EDGE-R. So I just have gene 1, that first gene that was called significant. Here were the 3 read counts for the females and the 3 read counts for the males, and you can see a pretty clear shift. So it's not surprising that we would have got a really small p-value for that gene, which would translate to a small FDR estimate. That's the same for all 4 of these. If I made this kind of picture for the EDGE-R, I would have much higher scale. I'd have 3 numbers, 2 numbers, and then 1 number way away from the others. Looks like an outlier. So DE-seq is nicer than EDGE-R, at least in respect to its ability to guard against that kind of behavior, outlying values. Here's the histogram of the p-values, and it looks a little bit weird. If there were no differential expression, we'd again expect that to be flat. We certainly don't expect there to be a peak in the middle or a peak at the right. We saw a peak at the right with EDGE-R. This looks pretty flat, but there is a peak in the middle. It turns out that that peak in the middle may just be due to low read counts. So I didn't put that plot in here. I think I did in the NGS script. So I might be able to get rid of that peak by filtering out genes that have relatively low p-values or relatively low overall read counts. DE-seq does automatically filter out low read counts. If it's too low read counts, it'll give you a p-value of NA. So here are genes that were given read counts of NA. So let's see, according to the documentation, p-values of NA are for genes with low read counts or for genes that are deemed to be outliers. These were all the genes that fit that criterion. Some of them were very low read counts. Some of them were called outliers, and not always clear to the naked eye why they would be called outliers. Many of these end up being, I think I have it in the script further down, many of these end up being the genes that were called statistically significant by edge R. For example, this guy has a single outlying value that's pretty obvious to the naked eye. Here's one that seems to have a single outlying value that's pretty obvious, and so on. But all of these genes were given NA p-values. Okay, and then the last method that we've considered for differential expression analysis with NGS data was lemma. Lemma was designed for microarray data, so continuous data where a normality assumption or t-distribution assumption is reasonable, or that kind of makes sense as a starting point at least. We don't have continuous data, but lemma has an associated transformation that was published in another paper called VOOM. And VOOM is for turning the count data into basically continuous data. It's an alternative to the R-log transformation for DE-seq2. Remember that with lemma, it wants to work with what's called a design matrix. And last time we met a design matrix. Here is a design matrix for our Gilead data. So these were liver tissue data, where we had 3 females and 3 males. So I showed you last time that in a 2-class problem, like females and males, you could write down a model that says expected read count is equal to, or expected intensity if I'm dealing with continuous data, is equal to beta 0 plus beta 1 times an indicator variable, 0 or 1, depending on which comparison group you're in. In this case, it might be 1 for male. So that beta 1 is the parameter of interest. It's the mean difference between females and males, or males and females. And I would have a separate model like that for each of the K genes. One way to represent a model like that is to say the vector Y for gene K is equal to capital X, a model matrix or a design matrix, times beta, a vector of the coefficients. So beta would be a 2-vector, beta 0 and beta 1. Capital X, the design or model matrix, would look like this. It's N by P, or it's N by, let's say, Q, where Q is the number of parameters in the model. In our case, we just have an intercept and we have a coefficient for gender. So we have 2 coefficients. The first is the intercept, and that's what's represented in the first column. And every single individual has the intercept in its model. So gene or individual 1, I would model with beta 0 plus beta 1 times either 0 or 1, depending on whether that individual is female or male. So this is part of that vector/matrix representation of the model. That's what a design matrix is. It's just 1s down the column in our case, and 0s and 1s depending on whether these 6 individuals were from the female or male group. More generally, a design matrix would have or could have more than 2 columns. If we had gender and we had age and we had race and we had a treatment variable, I'd have different columns for representing those additional covariates in the model. But with just a 2-class problem, it's very simple like this. VOOM transformation is done with the VOOM function, and then we use 2 functions from lemma to do the actual differential expression analysis. So LMFit does a linear model. So LM in R is a generic function for doing linear models, regression. So I provide the continuous version of my data, that's my response, and I provide a design matrix, and with that it can fit linear models. The E-base function, so that would give me beta coefficients. I'd have a beta, remember beta 1 is the parameter of interest, that's the mean difference between males and females for each of the genes. So I'd have a bunch of beta 1 hats. I would also have a bunch of estimated standard errors for those beta 1 hats based on least squares regression. But these methods, lemma and DESeq2 and EdgeR, do that moderation trick where they take the standard errors gene by gene and they shrink them towards a common standard error to standardize them, to regularize them, to limit the variability. So it's a bias variance trade-off. We accept a little bit of bias, expecting that the increase or decrease in variance will overall be a benefit. That's what happens in the eBayes function. So these things together compute p-values and false discovery rates for each of the genes. I can pull out the information, the FDRs with the top table function, and here's what it looks like. It looks kind of weird in this example. Lemma FDRs head lemma FDRs class lemma FDRs So here are, for the first 6 genes, their information. So I think these are ordered by p-value. So these were the top 6 genes. Small p-values. Interestingly, though, the FDRs were estimated all to be, I think, the very same number, but definitely none of them are less than 0.95. So FDR is a number between 0 and 1, just like a p-value. Smaller numbers indicate greater confidence in calling that feature different between conditions. And for some kind of odd reason, we have no FDRs less than 0.95. Here are the sample quantiles of those FDRs. And yeah, they're not all exactly the same number, but the minimum is 0.9538. So I wouldn't be happy with this analysis. In this particular data set, if I tried these 3 techniques, I'd go hang my hat on DESeq2. It seems to do the most sensible thing. Here's the histogram of the raw p-values, not the FDRs, but the raw p-values for lemma, and it does not suggest anything strange. It looks like a reasonable shape, but it certainly does not suggest that there's anything interesting in the data. More consistent with what we saw with DESeq2. DESeq2, for all those thousands of genes, searched for differential expression and only found 3. Lemma searched for differential expression among them all and didn't happen to find any. So it's not surprising that this looks virtually flat. I would expect a peak over on the left if there's a substantial number of differentially expressed features. If there's only a handful, it may look flat, basically like this example. Here's a comparison of those p-value histograms, just to put them side by side. EdgeR had that odd peak at the right, lots of p-values equal to 1, definitely looks unusual. DESeq2 looked mostly uniform, but it's got an unusual shape to it, increasing towards the right with a big peak in the middle. Might be able to remedy that by filtering out low recount genes. And then lemma looked mostly reasonable, some strange behavior, but mostly uniform between 0 and 1. So these 3 methods are obviously doing different things. The first 2 are based on the same assumptions, negative binomial read counts, but they handle those data in their own ways. They have their own normalization routines, filtering routines, outlier detection routines, and that translates to big differences potentially on the same data set. Ideally, there would be, if you have 3 flavors of methods that are basically doing the same thing, there would be some variability from method to method, but there'd be a lot of overlap in their overall conclusions. It doesn't really happen here. Lemma didn't find anything interesting DE-seq2 barely found anything interesting. Edge-R found a fair amount interesting. So here's a comparison of DE-seq2 to Edge-R. Curious to know, of the 4 genes that DE-seq2 called interesting, did they show up in Edge-R's list of interesting genes? So what I'm doing is it names DE-seq2 significant are the gene names for those 4 genes called interesting by DE-seq2. Names Edge-R significant are the names for Edge-R, so there's 63 of these. And I want to know, are these 4 contained in these 63? Do they overlap? And so the command you can use is %in%. So that checks component-wise the left vector whether each entry is contained in the right vector. And it gives me trues and falses for each of those 4 gene names. 3 out of the 4 DE-seq2 genes were called statistically significant by Edge-R. Here are the FDR estimates for all of the genes called significant by Edge-R. These are the DE-seq2 FDR estimates for all of those Edge-R significant genes. And what stands out is that there's lots of NAs. So I again think that those NAs are there because DE-seq2 said those genes have outlying values in them. So that makes some sense. I don't really like those genes anyway because of those outlying values. And the rest of them, except for this gene and that gene and I thought there should be another one. Oh, this gene. All of the FDR estimates are well above 1, or well above the threshold of 0.1.